Hi everyone, this is the Algebra 1A Semester 1 exam review, and this is the second part of the Chapter 2 portion. So this will cover number 7 through whatever the last problem is, 7 through 15 in the Chapter 2 part of the review packet. Okay, so starting with number 7. If x varies directly with t, what will happen to x when t is tripled? This is using what's called the fundamental theorem of variation. So I'm going to go ahead and set this up in a variation equation like we normally do. So this would translate as x equals k times t. Okay, direct variation means I'm using multiplication. And so what I want to know is if I multiply the t by 3, what's going to happen over here to the x? Okay, so first of all, because it's direct variation, anytime it's direct, whatever operation is happening here will happen over here as well. So if this is multiplication, there's going to be multiplication over here on the left. And then because t doesn't have any exponents on it, this 3 is just going to stay a 3. Okay, so as far as an answer, we could just say that x is going to get multiplied by 3, just like the t is. Multiplied by 3. Now, if that t had had a power on it, if it had been x squared or x cubed, then what would happen over here is it would be multiplied by 3 to whatever power the t was being raised to. So if this was a t squared, this would actually get multiplied by 9. Okay? All right, next question is very similar. If y varies inversely with x, so again, I'm going to take this and turn it into a variation equation. And inverse variation looks like this. Okay, so if y equals k over x, what happens to y when x is halved? So really what I'm saying is I'm going to take this x and divide by 2. Now I'm dealing with inverse variation. So with inverse variation, everything works the opposite on the opposite side. So if this is division over here, what I'm really going to end up with over here is multiplication. Okay, so it's opposite of each other when I'm working with inverse variation. Again, x doesn't have any powers, so nothing is going to happen to this 2. It's just going to end up being multiplied by 2. So I would say y is going to get multiplied by 2. Okay, the next question is very similar to the other two. It's sort of a real-life application, but we can approach the problem the exact same way. So the intensity of light varies inversely with the square of the distance. So before I even read any further, I'm going to translate that into a formula. So the intensity of light varies inversely with the square of the distance. Okay, so there's that sentence in symbols. What happens to the intensity if the distance is doubled? So what happens if I take this and I multiply by 2? Well, once again, I'm working with inverse variation. So when I have multiplication over here, I know I'm going to be dealing with division over here. Okay? And I'm going to end up writing that. Well, that's okay. And because this d has a square on it, this 2, when it applies over here, is going to end up getting squared as well. So really on this side, I'm going to end up dividing by 2 squared. Okay? So I could say the intensity gets divided by 4. Okay? So again, that 2 became a 4 because of the squaring that was going on. If that had been a power of 3, this would have ended up being an 8. Okay? And you've got the multiplying and the dividing because of the inverse variation. Okay, looking at number 10, it's very helpful if you already know these graphs from the table that we did on the previous page. I'm going to actually start with the second question and just write a general variation equation to match each one. So this first one is a parabola, which means this is direct variation squared. Okay. This is a hyperbola with both branches pointing downwards, so it's going to be y equals k over x squared. Anytime they both point in the same direction, I know I'm going to have an x squared in there. And this one's similar, except you've got them across from each other like this instead of both pointing in the same direction. So this is regular old inverse variation. This is k over x. Now I want to know, based on the pictures, what do I know the k values must be? So this one is pointing upward. Okay, so that tells me that k must be positive. Okay. Normally, this graph also points upward, so the fact that it's pointing downward today tells me that k here must be negative. And then this graph is typically, if I were to just graph this normally, in the first and the third quadrant. So the fact that it's flipped also tells me that k is negative. Okay, on to 11. And in 11, we're talking about some limits. All right, this is worded a little differently, but otherwise it's really the same question as like number 1 in this section. So what is the limit of y as x approaches infinity? So what that's saying is as you walk out on the x-axis towards infinity, so infinity would be in this direction, as I go out and out forever this way, what's happening to the y values on my graph? Well, y is the up and down, okay? And if you look at this graph, it's going to go up and up and up forever, all right? So y would approach positive infinity, okay? Because it's going upward forever and ever and ever, okay? Now, what is the limit of y as x approaches negative infinity? So negative infinity, same concept, except you're going in the negative direction forever and ever. So this would be negative infinity. As I look at my graph, as I move in this direction, my graph is still going upward in a positive direction, okay? So even though I'm going to negative infinity on the x-axis, my y's are still going in the positive direction. So I would say y approaches positive infinity here as well. Okay? Okay, let's go on to the back of this page. Okay, so same question, different graph. This time x goes out to infinity, so that'd be here. So what happens to my y values as I walk forever and ever and ever? You'll see that this time, instead of going upward forever, this is going down forever, but it's not ever passing this line. It's getting closer and closer and closer to that line, and if I pulled this way out to infinity, it's going to be awfully, awfully close, but never actually touch. And so you have to think about, what is the y value of that line that it's never crossing, okay? And that line represents y equals 0. So we would say y approaches 0. And then really the same thing for negative infinity. So as I go out forever and ever and ever to the left, this graph is going to get closer and closer to that line as well. So y would also approach 0. Now don't get trapped thinking these two are always going to be the same, because depending on the graph they may or may not be. It just so happened in these two examples they were. Okay, 13. W varies jointly with x and z. This works just like all your other types of variation. Joint variation is direct variation, but it's just direct. Whoops, I can't spell direct while I'm talking. It's direct variation with multiple variables. So I would translate this by saying W equals K times X times Z. And then I'm going to plug in these three that I know. I'm going to plug in 12, 4, and 2 to solve for my K value. Let's see, X is 4, Z is 2. That's really going to be an 8, so I end up with 12 equals 8K. And then I'm going to divide on both sides by 8, and I end up with 1.5 as a K value. And now I'm going to take that K value and plug it back into this formula. So now I know that I can get any other combination by doing 1.5 times X times Z. So now I'm going to take the X and the Z that they give me and use that to find W. So W would equal 1.5 times 3 times 2. That's 1.5 times 6, which is 9. So W equals 9. Okay, so it works like just all the other variation problems, it just you're working with more numbers. All right, let's take a look at 14. This is what's called combined variation, which is similar to joint variation, except now we can mix it up. Sometimes we might have direct, sometimes we might have inverse, whereas joint is all direct. So m varies directly with n, so I'm just going to start with this. M varies directly with m. And inversely, which means I'm dividing, with the square of p. So notice I'm using all the same k value. I'm just setting one up as direct and one up as inverse. Again, I am going to plug the m, the n, and the p in. So let's see, m is 4, n is 12, and p is 3, so that's 3 squared. If I simplify this a little bit, I'm going to be off the screen here in a second. I get 4 equals 12k over 9. And remember, you can get rid of this whole fraction right here by multiplying by its reciprocal. So I'm going to multiply by 9 over 12, multiply by 9 over 12. And I know this looks scary over here, but this is really just 9 times 4 divided by 12. So that's 36 divided by 12, which is 3. And then once you know your k value, just like before, I'm going to say now I know that m equals 3 times n over p squared. And now I can plug in my n equals 8 and my p equals 4. So m equals 3 times 8 over 4 squared. That's 24 over 16, which, I believe is 3 over 2, which is 1.5. So 1.5 or 3 over 2 would work there. Okay, and that's it for that one. Okay, on to the next page. So we have a couple of different sets of data, but they're related to one another. We're looking at the relationship between power, resistance, and current. Okay. The first one is looking at resistance, the effects of resistance on the power output. Okay. And it tells us to create a scatter plot of these data, really just in your calculator. Okay, really my whole mission here is just to see the shape of the graph. So quick review on how to do that. I know we just did it on the previous page, but you're going to go to Stat and Edit, which is option number 1. Got some stuff in mind, so I'm going to clear it out. So in list 2, list 1, I'm putting this first set of numbers. And list 2, I'm putting the second set. And then to get my scatter plot, to be able to see these points, I'm going to go to y equals. Again, clear out anything that happens to be there. You want to go up and turn your plot 1 on, and all that does is tell your calculator to look in your data plots or your stat plots for the data instead of looking for an equation here. And then I'm going to go to zoom, and I believe it's number 9, zoom stat, and that's what's going to tell your calculator to automatically adjust the window to fit that data. Okay, and there's my scatter plot. So that's what I'm looking for. And it says, how does P vary with R? Well, this is linear, right? So we know this is direct variation. Okay. And I'm going to go one step further. I'm actually going to write just a general variation equation. We know that if this is direct variation and it's linear, this is like my y. This is my dependent value. So I'm going to start with that. And I'm going to say this is P equals K times R. Okay, and I can tell that again, once I know this is linear, I know that this is what my equation is going to look like. Okay, now we're going to do the same thing again, except with a different set of data. So again, I'm going to go Stat, Edit. I'm going to clear my lists, which means I go up to the top and I hit Clear and Enter. And then I'm going to enter in this list. So 2, 3, 4, 5, 6, 7. in that first list. The second set of numbers goes here. Okay. And I should already have my plots turned on. Okay, so under y equals, if you turned it on last time, it should still be on. But I am going to have to redo my zoom stat because we're now fitting a new set of data here. So I'm going to go zoom in number 9. And this one, it's a little bit hard to tell. And maybe the zoom stat, maybe we're zoomed in a little too far. But there is actually a curve here. Okay, this is actually like half of a parabola. It's just a little bit tough to see. That's still considered to be direct variation, but it's direct square variation. Okay, so we could say that it varies with the square of the amps, or the current, I guess I should say. So if I were to write this in an equation using direct square variation, it would look like this. P equals K times I squared. The square is how we get it to form that parabola shape. The reason I did these is because down here in part C, it wants me to write one giant equation that contains all of those letters. And all I'm going to do is take these two equations that I wrote above and smash them together. So it's going to start with a P, it's going to have a K, and these are both multiplications, so I can just multiply them both. It would be R and I squared. And that's what your final equation would end up looking like there. And that's all you have to do for that. We could plug numbers in and find the K value and write a more specific equation, but the question did just ask for a general equation, so we're good to go there. Okay? And that does it for Chapter 2. So I'm going to continue working and hopefully get some other chapters posted up there tonight. So stay tuned.